Hello, night travelers. Welcome to the Night Observer channel, a place where gentle souls come to find relaxation, comfort, and peaceful sleep, accompanied by quiet reflections on the mysteries of the universe. Here, beneath a star-filled sky, we kindle a small bonfire to welcome you, to warm your spirit, and to share stories about the universe, about distant planets, enigmatic stars, radiant cosmic dust, and the Milky Way, filled with secrets that lie just before our eyes. You will hear the majestic symphony the Milky Way has played for more than 13 billion years, a melody that will continue without end. All you need to do is breathe and let your body rest upon your bed or sofa, allowing your soul to drift with the silent harmonies of the cosmos, so your mind and body may finally unwind after a long day. Now, let our journey begin through the Milky Way, where we listen together to its everlasting song. Until this day, scientists still do not know exactly how the Milky Way was formed. Yet one thing is certain: it did not begin with a single explosive event like the Big Bang, not with a thunderous drumbeat, nor a resounding clash of cymbals. Instead, it began with slow, whispering melodies that gradually intertwined. These gentle melodies were born from countless smaller worlds colliding with one another, their remnants merging to create a larger, grander galaxy. And that is our Milky Way, a vast symphony in which every collision leaves a lasting signature. Let me ask you a question. When you listen to music, what do you hear? A familiar, harmonious tune? A graceful rhythm? Or perhaps you can picture the instruments shaping each melody. Can you sense each note resonating? All of these are true. Yet there is something always present, something we seldom notice: the musical staff. Without it, music cannot exist. And the musical staff of the Milky Way is dark matter. From the very beginning, dark matter has been the framework of the universe's structure. It is extraordinary. Scientists estimate that it accounts for about 95% of the Milky Way's mass. It does not interact with electromagnetic radiation, does not emit light, does not absorb it, and does not reflect it. In essence, it is invisible to us, just as the musical staff remains unseen, yet quietly supports every piece of music ever written. Imagine the Milky Way as a delicate silver disk, glowing with a brilliant center and fading gently toward its edges. According to classical Newtonian gravity, the stars and gas clouds at the farthest reaches of this vast disk should rotate much more slowly than those near the core. If they moved too quickly, they would be cast out into space, much like a kite breaking free from its string. This is similar to our own solar system, where the planets most distant from the sun rotate far more slowly than those closer to the center. Yet astronomers have uncovered a remarkable truth. The rotation speed of stars and gas, especially through radio observations of the 21-centimeter emissions from atomic hydrogen, reveals that the Milky Way's rotation curve remains nearly flat. In other words, the stars along the outer rim of this silver disk maintain unexpectedly high speeds, showing no sign of slowing with distance. This tells us that something larger than the visible Milky Way must be holding the galaxy together. Even today, many experiments have not been able to directly confirm the presence of dark matter. However, its existence is inferred from its gravitational effects on the motion of stars and gas within galaxies. The significant gap between the observed rotation speeds and the speeds predicted using only visible matter, stars and luminous gas, strongly supports the dark matter hypothesis. It is real, and its definitive confirmation seems only a matter of time, especially as technology continues to advance. In modern cosmological models, galaxies are believed to take shape within a vast and hypothetical structure known as a dark matter halo. Our own galaxy is thought to rest gently inside such a halo, an immense, almost spherical envelope of dark matter. It is so expansive that it surrounds the entire galactic disk, stretching far beyond the faintest edge of the Milky Way. Scientists estimate that dark matter makes up nearly 95% of our galaxy's mass. It is a quiet force, yet it governs the movement of the entire galaxy. It keeps stars and planets from straying from their paths. It is the musical staff that holds star systems in place, playing a silent, steady melody. Without dark matter, those systems would drift, and the music of the cosmos would fall into disorder, perhaps losing its harmony altogether. The staff exists, and creation begins to write its first notes. Upon this vast musical staff called dark matter lie the witnesses of the universe's earliest dawn, the ultra-metal-poor stars. They are the first notes of the cosmic composition, guardians of the oldest memories of the Milky Way. Formed from the most ancient materials, they are composed of only hydrogen and helium, fossils of light, carrying the imprint of a time before the universe had yet forged heavier elements, what astronomers now call metals. To understand the history of the Milky Way, scientists must rely on a method known as galactic archaeology. The name may sound unusual, even a little mysterious, yet it is a real and essential field of research. Galactic archaeology seeks to unravel the formation and evolution of our galaxy. Just as archaeologists on Earth study ancient relics, astronomers examine old stars and their orbits to trace the history of mergers, collisions, and star-forming events that shaped the Milky Way. Through this work, they uncover extraordinary insights. They follow the faint fingerprints left behind by each star. For every star carries a unique elemental signature, imprinted at the moment of its birth. In the earliest moments after the Big Bang, only the lightest elements came into existence: hydrogen, helium, deuterium, and lithium-7. Some supernovae may have formed during this early era. The heavier elements, what astronomers call metals, were created later through the thermonuclear reactions inside ancient stars before they ended their lives in brilliant explosions. Scientists estimate that roughly 1 billion years after the Big Bang, metal-poor stars began to form from the primordial material left behind. Some of these stars contain less than 1/10,000th of the iron found in our Sun. They are the elders of the Milky Way, pioneers born from the universe's earliest supernovae. A remarkable example is J1808-5104, an extremely metal-poor binary system in the constellation Angel, a single spectral binary star with a very small companion. It is an unusual object, low in mass, low in metals, and astonishingly old. At approximately 13.53 billion years of age, it may be among the very first stars, formed almost entirely from material created in the Big Bang. It belongs to the Milky Way's thin disk and stands as the oldest known thin disk star, older by several billion years than most estimates of the thin disk itself. Another remarkable example is HD 140283, often called Methuselah. It is a metal-poor star resting 190 light-years from Earth in the constellation Libra near Ophiuchus. This star is among the oldest known in the universe, with a metal content far lower than that of the Sun. In 2013, using the Hubble Space Telescope's interferometer, astronomer Howard Bond and his team estimated its age to be about 14.46 billion years. This creates an intriguing paradox, for we know the universe is approximately 13.8 billion years old. Yet scientists explain this discrepancy as a reflection of the limitations in our understanding at the time, a difference considered acceptable. It also inspired several hypotheses, including the thought that many metal-poor stars may have existed even before the universe fully formed. Scattered throughout the galactic halo are the globular clusters, ancient spheres containing hundreds of thousands of stars, held tightly together by gravity. They orbit the galactic center like distant satellites. These clusters are home to some of the oldest stars ever observed, many so ancient that they were already shining before the Milky Way itself fully took shape. But whatever the explanations may be, one truth remains. These metal-poor stars are the very first notes of our galaxy. They are like the small bonfire we gather around tonight, bright, guiding, and full of quiet meaning. They illuminate the path that carried humanity from its earliest beginnings to the dawn of scientific understanding. From the darkest moments of the universe's youth to the first glimmers of light, they lead our thoughts into slow, gentle melodies that have endured for millions of years, laying the foundation for the endless epic of the Milky Way. Surely, at this very moment, you may find yourself drifting into the first sounds of the universe, wrapped in gentle, unhurried melodies, and perhaps sleep is already approaching. But if your eyes are still open, then let us continue to the next chapter, where the soft harmonies begin to fade, giving way to a quicker, more forceful rhythm. The Milky Way's grand symphony has not always been smooth and serene. Across billions of years, it has produced fierce, piercing notes. To us, the Milky Way may appear breathtaking, a vast canvas of hundreds of billions of stars, a source of beauty and artistic inspiration. Remember that even its name, the Milky Way, was born from ancient Greek mythology. Yet to astronomers, this galaxy is something far more formidable, a kind of cosmic monster. The comparison may stir your imagination, but indeed, to astronomers, the Milky Way behaves like a ravenous giant. It is one of the oldest and largest galaxies, and to reach its current extraordinary size, scientists believe it endured more than 20 galactic engulfment events during its early years. They also believe the Milky Way has grown by swallowing and dismantling smaller dwarf galaxies, drawing their stars into its disk and halo. And this is not mere speculation. In 2013, the European Space Agency, ESA, launched the Gaia satellite, designed to unravel the complexity of galaxies by gathering precise and comprehensive data. Gaia was created with a single purpose: to map celestial bodies around Earth and across the universe with unprecedented accuracy. Since 2014, using its specialized telescopes, it has compiled a vast dataset detailing the position, distance, and motion of 1.5 billion stars, allowing researchers to probe the past and present structure of galaxies with remarkable clarity. Then, in 2018, Gaia revealed the Gaia Enceladus galaxy cluster, the remnant of a monumental merger with the dwarf galaxy Enceladus. This cluster is sometimes nicknamed the sausage cluster, due to its distinctive shape in the velocity space diagram. Within it, Gaia identified nearly 30,000 stars whose motions are unlike most others in the Milky Way. Instead of circling the galaxy, they move in long, sweeping paths, in and out. This system is linked to at least 13 globular clusters and the formation of the Milky Way's thick disk, an older, heavier, and more metal-poor layer of stars. After the thick disk ceased forming stars, a quiet interval followed, until fresh gas settled and created the thin disk, the birthplace of our sun 4.6 billion years ago. Like the climax of a musical composition, the Gaia-Enceladus merger echoed through the cosmos with the violent resonance of a collision. Scientists believe that this encounter between the Milky Way and the dwarf galaxy Enceladus occurred about 10 billion years ago, profoundly reshaping the structure and early evolution of our galaxy. Most of the stars drawn in by the Milky Way now reside in its outer halo. This cosmic impact is also thought to have caused the original galactic disk to swell, giving rise to what we now call the thick disk, a pivotal moment that, according to some cosmological models, partially disrupted the galaxy's earliest form. Understanding the Milky Way's disks allows us to trace its age and its long history. Though the Milky Way is a disk galaxy, it is composed of two major layers, the thick disk and the thin disk, each with distinct chemical and physical stories. The thick disk formed extraordinarily early, roughly 800 million years after the Big Bang, and spans a height of about 2,000 to 3,600 light-years. Its stars are generally older and poorer in metals than those of the thin disk. They carry abundant alpha elements, suggesting they were born in an era of rapid, intense star formation. During the age when the thick disk dominated the Milky Way, iron levels surged nearly 30-fold due to stellar explosions, enriched gases, and the constant birth of new stars. Star formation in the thick disk halted around 8 billion years ago. This cessation, this quiet pause, is known as the time gap. In classical cosmological models, the gap lasts about 1 billion years. In modern models, closer to 4 billion. The interruption was caused by the Gaia-Enceladus merger, when the echoes of the collision reverberated across the universe. Scientists believe this event heated the galaxy's gaseous environment, leaving the thick disk too warm to continue forming stars at its earlier pace. During the intense peak of the merger, streams of fresh gas from outside the galaxy began to settle, like musical notes calming after a storm of powerful rhythms. This accretion occurred slowly, with a gentler and less efficient rate of star formation. From this quieting phase, the thin disk emerged, only about 2,000 light-years thick, yet still giving birth to new stars even today. During the intense peak of the merger, streams of fresh gas from outside the galaxy began to settle, like musical notes calming after a storm of powerful rhythms. This accretion occurred slowly, with a gentler and less efficient rate of star formation. From this quieting phase, the thin disk emerged, only about 2,000 light-years thick, yet still giving birth to new stars even today. Among them is our Sun, formed about 4.6 billion years ago. The Gaia-Enceladus merger is regarded as the last and largest of these ancient encounters, but it was far from the only one. The Milky Way still carries the scars of other mergers, events scientists believe may have occurred as many as 6 times. One of the most remarkable was the collision with the ancient dwarf galaxy Kraken, about 11 billion years ago, when the Milky Way was only a quarter of its present size. This encounter is thought to have been even more violent than the Gaia-Enceladus event. Another dwarf galaxy, Sagittarius, was gradually torn apart by the Milky Way's immense gravitational pull, leaving behind long currents of stars, graceful celestial ribbons that sweep across the sky. Among them are the Sagittarius Stream, the Helmi Stream, the Aquarius Stream, all shaped by tidal forces, all remnants of the powerful, dramatic merging melodies that began billions of years ago. The Milky Way is not solitary, nor is it still. It is a composite being, absorbing, reshaping, and sometimes consuming the galaxies around it, weaving the melodies of countless systems into its own vast symphony. And within this grand sequence of cosmic events, humanity appeared on Earth, a small yet remarkable note blending gently into the larger music of the Milky Way. Even as we sit here now, gathered by this warm fire, that great epic continues to unfold. You have traveled through the climactic symphony of the universe, letting your thoughts drift among immense collisions and ancient rhythms. Yet the firelight here remains steady and warm, allowing you to rest, to dream, and to witness the quiet flow of galactic history. You may sense how a single day of your life is small compared to the universe, and it is precisely because of this that every moment becomes profoundly precious. To let sleep approach, to let your mind sink into the gentle stillness of the cosmos, is a comforting thing. But if you are still here, still listening, then come with us, as we step into the eternal rhythm of the Milky Way. After the melodious beginnings and the violent climax of the Great Collision, the Milky Way now settles into a steady, captivating rhythm, a rhythm that hides countless secrets within its vast expanse. Take a moment to look at the Milky Way. It is a grand, spiral galaxy. Contrary to what we might once have believed, this immense structure is not fixed in place. It has been slowly, continuously rotating through space for more than 13 billion years. Even now, as you listen to these words, the Milky Way drifts onward in a silent motion, a movement too subtle for the human senses to detect. From afar, it presents itself as a serene, orderly spiral, yet from within, it is a realm of ceaseless motion, like great vessels gliding through the dark, held in balance by time and gravity. And with dark matter as its unseen orchestration, planets and stars together create a majestic cosmic symphony. To understand the rhythm of the Milky Way, scientists describe its motion through what they call rotational curves, graphs that show the orbital speeds of stars and interstellar gas in relation to their distance from the galactic center. Consider the solar system, humanity's own sheltered rooftop. It lies approximately 27,000 light-years from the center, and it, too, moves with remarkable speed, about 230 kilometers per second. It may sound unbelievable, but you are traveling with it at that very pace. Yet, despite this astonishing velocity, the solar system needs 225 million years to complete a single orbit. Since its formation 4.6 billion years ago, it has circled the galactic center only about 20 times, 20 slow, sweeping revolutions. As mentioned earlier, scientists once expected that stars farther from the galactic center would rotate more slowly, following the familiar laws of orbital mechanics. But observations told another story. Using radio measurements of atomic hydrogen at 21 centimeters, astronomers discovered that the rotation curves of most spiral galaxies, including our own, do not decline, they flatten. This means that the rotation speed of most stars remains nearly constant, between 200 and 220 kilometers per second, regardless of their distance from the center. Such findings strongly support the idea of an unseen presence, dark matter, and suggest that our galaxy is enveloped in a vast, invisible halo of it, granting the Milky Way its remarkable stability. To us, the solar system feels immense, a grand structure in its own right. Yet in truth, it is only a small part of the Orion Cygnus arm, named after Orion, the most familiar constellation in the night sky. And even this arm, with all its quiet beauty, is but a modest branch of the Milky Way. The Milky Way holds two great sweeping arms, the Perseus arm and the Scutum Centaurus arm. Alongside them lie the smaller ones, the Carina Sagittarius arm, the Norma arm, and tucked gently within, the Orion Cygnus arm, where our solar system drifts. Beyond these are the delicate spurs extending outward, like subtle brushstrokes. These spiral arms mark regions of higher density, places where matter gathers and ignites the birth of new stars. One might imagine the spiral arms as fixed, rigid structures, yet they are, in truth, moving patterns, density waves. Stars and clouds of gas pass through them, drawn into their rhythm as if carried by ocean swells. You can picture them as countless points gliding along a crowded highway, each slowing as they enter the denser region ahead, or as musical phrases, single notes, double notes, intricate motifs, woven seamlessly into a vast, expressive composition. As these density waves sweep through, they compress cold gas clouds, giving rise to stellar nurseries that briefly illuminate the galaxy with young, radiant blue light. Although we have journeyed through the Milky Way and listened to its grand harmonies, you and I have only heard a small fragment of its full song. Interstellar dust, cosmic dust composed largely of graphite and silicates, lies between the stars. Within our galaxy, it gathers into clouds, nebulae, and distant structures like the Oort cloud. This dust absorbs starlight, dimming it by an average of 1 magnitude per kiloparsec along the galactic plane, and so we see only a narrow portion of the Milky Way's true brilliance. Within this vast symphony, there exist small, curious, and profoundly important notes that help humanity understand the universe. Among them are cosmic rays, high-energy particles born from supernovae and far-off galaxies, passing through space and through us every second. And there are radio waves whispered from gas clouds, from pulsars, and from the cool breath of drifting hydrogen. Through them, we trace the structure of galaxies across the dark. Among the most remarkable celestial objects are pulsars, neutron stars that serve as the universe's own clockwork, born from the remnants of massive stars that have ended their lives in brilliant supernovae. These stars are unimaginably dense and astonishingly small. They rotate with extraordinary speed, sometimes hundreds of times per second, as in the case of pulsars, spinning at 716 revolutions each second. Their beams of radiation sweep across Earth with such consistency that we perceive them as steady, rhythmic pulses. What is truly extraordinary is their precision. The flickering cycle of a pulsar is so regular that it surpasses even the accuracy of atomic clocks. Musicians rely on metronomes to keep their music steady and true. Pulsars, in their distant solitude, are like vast cosmic metronomes guiding the rhythm of the Milky Way itself. Because of this remarkable stability, scientists use pulsars as timekeepers on a cosmic scale, measuring distances, testing gravity, and tracing signals not in minutes or days, but across vast epochs. By now, perhaps you find yourself drifting gently through the Milky Way's spiral arms, allowing your thoughts to wander among its radiant clusters and immense drifting clouds of dust. Maybe you have even begun to fall asleep imagining the steady glow of pulsars, like lighthouses casting their beams across the deep ocean of the universe. But if you are still with me, gathered here beside this warm, quiet fire, then let us continue our journey toward the heart of the galaxy. We have spoken of the motion of the solar system within the Milky Way's arms. Just as there is an old saying that all roads lead to Rome, in our galaxy, all orbits slowly draw toward the galactic center, a dense region filled with ancient, bulging stars. About 26,000 light-years from the Sun lies Sagittarius A, or SGR-A, near the boundary of the constellations Sagittarius and Scorpio. Observations of the star known as Source 2, which moves in a tight orbit around SGR-A star, together with decades of collected data, reveal the unmistakable presence of a supermassive black hole at the galaxy's core. Every melody has a composer, every orchestra needs a conductor, and the Milky Way's vast symphony is guided by its conductor, SGR-A. We often marvel at the mass of the Sun, so great that ordinary measures feel inadequate to describe it. Yet SGR-A possesses a mass 4.3 million times greater. This value has been measured with extraordinary precision, more accurately than any other black hole candidate in the observable universe, by following the paths of nearby stars, especially the star known as Source 2. Astronomers today still cannot observe the visible spectrum of SGR-A, for it lies behind a thick veil of dust and gas that scatters and absorbs much of its electromagnetic light. Several research teams are working to reconstruct its image in the radio spectrum, using vast, long baseline radio interferometers. From these efforts, its diameter is estimated to be around 28 quadrillion kilometers. Scientists also hope to capture SGR-A with far greater clarity through the Event Horizon Telescope, a global array of radio telescopes acting as one immense interferometer. With this project, they aim to test Einstein's theory of relativity more rigorously than ever before. And if future observations reveal any inconsistencies between theory and reality, researchers will need to determine the circumstances under which relativity may falter. Yet whatever our instruments can or cannot reveal, SGR-A remains at the center of the Milky Way. We cannot see it directly, but its gravitational pull acts like a silent conductor, guiding the stars around it at astonishing speeds. Despite its immense mass and influence, SGR-A is a compact radio source, its slow drift across the sky perfectly matching the solar system's orbit around the galactic center. It is, in every sense, the conductor of the Milky Way's rhythm, steady, quiet, and profoundly powerful, drawing the stars and planets into its gravitational score. The nearby stars circle it rapidly, most famously the star known as Source 2, moving as if obeying the gestures of a seasoned and respected maestro. And yet, this conductor is anything but flamboyant. Today, SGR-A is considered a radiatively inefficient black hole. Its luminosity is remarkably faint. Both its radio and X-ray emissions are only a tiny fraction of what would be expected from its Eddington luminosity. This subdued activity has led scientists to propose special accretion models, known as the advection-dominated accretion flow, to explain why so much of its energy seems hidden rather than radiated away. Moreover, the rate at which SGR-A gathers matter is extremely low. Only a small portion of the material it captures ever reaches the event horizon. This stands in contrast to the familiar image of black holes as ravenous beasts, endlessly consuming everything, including light, that ventures too close. Even without being a powerful or ostentatious conductor, SGR-A continues to astonish us with its quiet, subtle grace. Though faint, calm, and often described as sleeping, it occasionally reminds us that the Milky Way's great melody is still unfolding, and that it remains the one guiding it all. In 2010, NASA's Fermi Space Telescope revealed two mysterious structures in the central region of our galaxy, colossal shapes resembling the outstretched wings of a celestial creature. These formations, later called the Fermi bubbles, extend above and below the galactic center, each one filled with gas, dust, and gamma rays. Together, they span nearly 50,000 light-years, almost half the diameter of the Milky Way. Much later, scientists determined that about 6 million years ago, as SGRA drew matter toward its event horizon, it released two powerful jets of high-energy radiation. These jets raced outward from the galactic center at nearly the speed of light and over roughly 1 million years, carved out the vast Fermi bubbles. This discovery suggests that SGRA was once highly active, almost quasar-like, igniting a blazing chapter in the Milky Way's long symphony. Even now, SGRA occasionally brightens, sending out brief but brilliant flares, especially in X-ray and near-infrared wavelengths. These flares rise and fade within about an hour, indicating that their source lies in a remarkably compact region, perhaps no larger than 10 times the Schwarzschild radius. And in 2015, NASA's Chandra X-ray telescope witnessed something extraordinary. An X-ray flare 400 times brighter than usual, the most intense ever recorded from SGRA. Scientists believe this unusual burst may have been triggered by an asteroid plunging into the black hole, or by a sudden disturbance in the magnetic field lines threading through the gas spiraling inward. Observations from many telescopes reveal that SGRA flickers almost continuously, its faint flares rising and falling like quiet breaths. Recent results from the Event Horizon Telescope have uncovered a strong, organized spiral magnetic field encircling the edge of SGRA. This magnetic structure closely resembles that of the black hole in the center of the M87 galaxy, a giant elliptical galaxy in Virgo, 53 million light-years away. The similarity suggests that powerful magnetic fields may be a universal feature of black holes. It also implies the presence of a hidden stream of matter circulating within SGRA star. These delicate flares allow scientists to probe the plasma conditions extremely close to the black hole, offering deeper insight into one of the universe's most enigmatic realms. And now, the picture becomes clearer. The unseen yet steadfast framework of dark matter, the first gentle notes played by ancient metal-poor stars, the violent crescendo of galactic collisions that shook the cosmos billions of years ago, the luminous spiral arms carrying hundreds of thousands of stars like musicians, the neutron stars, those pulsars, twinkling like cosmic metronomes keeping time, and at the center of it all, the silent conductor, SGRA. From the small fire glowing here beside us, you have listened to the Milky Way's grand composition. Perhaps, somewhere along the way, you drifted into sleep. But if you are still here, still watching the flames dance softly before you, have you ever wondered whether the Milky Way itself is a living being, a vast organism that truly breathes? We now understand that the Milky Way does not simply produce music, it sings. Its song is its great breathing cycle. Interstellar dust shrouds immense regions of space, blocking visible light and giving the illusion of darkness. Yet that darkness is not emptiness. It is a cradle. It shelters the galaxy's most delicate voices. Cold gas and dust, only a few degrees above absolute zero, slowly collapse under their own weight, forming protostars, newborn stars still gathering material from the clouds that created them. From the coldest darkness, these stars rise in brilliant light, singing clear and youthful notes that blend seamlessly into the Milky Way's eternal harmony. And it is not only the protostars that sing. The Milky Way itself has a voice of its own. Violent supernovae erupt with currents of scorching matter, rising above and beyond the galactic disk to create what astronomers call the galactic fountain. The material they cast off forms immense, high-pressure, low-density bubbles of hot gas within the cooler, denser layer of dust and gas that surrounds the disk. Some of these bubbles drift far enough, upward or downward, to pierce the disk entirely, opening a chimney through which hot gas escapes into the halo, much like a geyser emerging from beneath the Earth. As this expelled gas cools, it slowly falls back into the disk under the pull of gravity, enriching it with heavy elements, what astronomers refer to as metals. This gentle cycle takes millions upon millions of years. The Milky Way does not merely rotate, it turns, it breathes, and it sings a flawless, eternal song. The most massive stars end their lives in supernovae, yet their ending is also a beginning. Their explosions scatter heavy elements, iron, gold, and others, into space, becoming the raw material for new generations of stars and worlds. Meanwhile, pulsars, the dense remnants of neutron stars, act as cosmic timekeepers. Their swift rotations send narrow beams of radiation sweeping through space, marking time not in hours or days, but in epochs. And still the Milky Way breathes, carrying within it the rising voices of new stars born each day. We owe our gratitude to the devoted scientists who have made it possible for us to hear the Milky Way's melody. A successful concert needs musicians, instruments, and a score, but it also needs the quiet skill of the sound and lighting teams who bring everything together. Scientists are the technicians who deliver this grand celestial performance to us, not only in sound, but also in images. You may have wondered how scientists, standing here on Earth, have managed to recreate the structure of the Milky Way. The Voyager 1 spacecraft, now drifting in interstellar space, is merely 24 billion kilometers away, about 24 light hours. From that distance, it is as though we are standing in the heart of an immense forest, seeing only the trees and leaves around us, unable to take in the forest as a whole, and above all, the visible light of the galaxy is veiled by interstellar dust. Yet humankind is a remarkable species. From the first glow of fire, we have drawn a boundless desire to understand, a flame that burns ceaselessly, guiding us into the vast and silent dark. The European Space Agency's Gaia spacecraft has quietly transformed the world of astronomy. For many decades, astronomical surveys could observe no more than 2 million stars. Yet Gaia has expanded that number to an astonishing 2 billion. More than simply counting them, Gaia has measured their positions, their motions, and their brightness, then woven all of this into a vivid, sharply defined three-dimensional map, quite different from the static star charts we once relied upon. This living three-dimensional portrait reveals streams of stars torn from ancient galaxies, traces the graceful warp of the galactic disk, and follows the sun's orbit with remarkable precision. Another of Gaia's remarkable achievements lies in its use of variable stars to measure cosmic distances. Certain well-known variables, Cepheids, RR Lyrae, possess a celebrated relationship between their brightness and their pulsation periods. By measuring how long it takes for a star to brighten and fade, astronomers can determine its true luminosity. Comparing that intrinsic brightness to how bright it appears from Earth allows them to calculate its distance. These stars become cosmic yardsticks, helping us chart the architecture and scale of the Milky Way. Through these refined measurements, Gaia has shown us that the Milky Way is not a still or silent structure, but a dynamic, breathing entity, its melodies constantly shifting across an ancient and sprawling canvas. Thanks to Gaia, we have learned of past galactic mergers, such as the dramatic Gaia Enceladus event, or the far older Kraken merger, which occurred some 11 billion years ago. Gaia has also detected the warping of the galactic disk and the flowing streams of stars surrounding it, revealing that our galaxy is still evolving, still responding to encounters with its satellite companions, including the large and small Magellanic Clouds. The Milky Way's melody is just that, quiet yet persistent and endlessly unfolding. Gaia has also taught us that not all stars remain in the place of their birth. Many wander, Some drift gently inward or outward under the pull of gravity. Even our own sun has traveled far from its birthplace over its 4.6 billion year lifetime. A few stars are cast out at extraordinary speeds, becoming hypervelocity stars, solitary travelers racing through the galaxy, like wandering musicians moving from city to city, carrying their own timeless songs. Night travelers, are you awake or drifting somewhere between waking and dreaming? If you are still here with us, gently close your eyes and let the warmth of the fire draw you into the living melodies of the Milky Way. Feel the echoing songs of fading stars, the clear rising voices of newborn suns. Sense the slow rhythmic breath of the galaxy itself and listen to its deep, resonant music, an ancient song that will endure for as long as time allows. You are a small soul floating among stardust, among luminous spiral arms and the quiet streams left behind by supernovae. And in that drifting, you may find yourself carried by a vast, cosmic symphony. You will hear the whispers of distant stars and see the scattered phrases of the Milky Way's melody gradually merge into one breathtaking harmony. If you are still awake and wish to accompany this melody to its final notes, then stay with me as we journey into the grand finale of the Milky Way's symphony. As we learned from the Gaia Observatory, the Milky Way is not fixed in place but constantly evolving. Its melody is refined over the ages, always needing new themes to weave into its ancient score. Though it has lived for 13 billion years and experienced many mergers, the galaxy continues to grow, deepening in complexity with each passing era. Even now, as you and I sit together beside this quiet fire, listening to stories of the distant universe, the Milky Way is gathering new material. Its growth takes many forms. Like a great lung, it continuously draws in gas from the intergalactic medium, the raw substance from which new stars are born. Sometimes this growth is gentle, as gas clouds slowly accumulate. At other times, it is more dramatic and forceful. The Milky Way steadily consumes its dwarf satellite galaxies, pulling them apart and drawing their stars into tidal streams that wrap around the galactic disk, much as it once did to the small galaxy Enceladus during the Gaia Enceladus event. Even now, the Sagittarius dwarf galaxy is being torn apart in a similar way. And beyond what we can see, invisible dark matter continues to feed the vast halo surrounding our galaxy. Because the Milky Way is always in motion, always reshaping itself, the galaxy we observe today is entirely different from the one seen by the dinosaurs 200 million years ago. And if humanity endures far into the future, our distant descendants will look up at a Milky Way transformed, built from ancient mergers, enriched by streams of wandering stars, and glowing with a disk more expansive and magnificent than the one we know now. We have spoken of rogue stars, those solitary travelers flung into space at astonishing speeds. These stars are often the remnants of binary systems torn apart by the immense gravity of the supermassive black hole SGR-A star at the galactic center. When one star is drawn into the black hole and vanishes beyond the event horizon, its companion is cast outward, hurled into the darkness at nearly 1 million kilometers per hour. At such a speed, it can break free from the Milky Way entirely. It then wanders alone, carrying with it the fading songs of the time it once danced with a partner. It will journey on, never to return. Their silent passage reminds us that even within the grand melody of the Milky Way, there are notes of separation and loss, melodies that once existed and will one day fade into the quiet of the universe. Most stars in the Milky Way orbit the center in a shared direction, but a few refuse to follow this familiar path. Some stars, especially those in the distant halo, travel in retrograde, moving opposite to the galaxy's overall rotation. These ancient wanderers were likely born in small galaxies long ago absorbed by the Milky Way. Their backward motion is a subtle, enduring signature of their foreign origin, a whisper carried across time. They are the lingering evidence of past mergers, powerful and turbulent movements that once echoed through the galaxy for hundreds of millions of years before growing silent again. The Milky Way is a vast engine of renewal. Stars live, shine, and die, and in their dying breaths, they return their essence to the galaxy. When massive stars reach the end of their lives, they erupt as magnificent supernovae. And in these cataclysms, they do not simply end, they create. They enrich the surrounding space with heavy elements such as iron and gold. Over time, this enriched material cools, gathers, and becomes the substance from which new stars, new planets, and perhaps even new forms of life are born. And here is something quietly profound. Every part of our bodies comes from these ancient galactic melodies. Every molecule within us was shaped by events that unfolded across the long history of the universe and the Milky Way itself. Even now, as you drift toward sleep, the galaxy continues its ceaseless transformation, renewing, reshaping, and composing its eternal song. The Milky Way's melody now drifts in a slow, almost timeless rhythm. Yet in the distant future, billions of years from tonight, a new and powerful movement will rise, grand, turbulent, and magnificent. In the night sky, a faint streak of light is already on its way, gliding silently toward us at 110 kilometers per second. It is Andromeda, a vast spiral galaxy 2 million light-years away. And in about 4.5 billion years, these two majestic spirals will meet in a cosmic embrace. Despite the word collision, this encounter will not resemble an earthly impact. The stars within each galaxy are separated by immense distances. Consider this: the closest star to Earth, apart from the Sun, is Proxima Centauri, 4.2 light-years away. If the Sun were the size of a ping-pong ball, Proxima Centauri would be a pea, placed some 40 trillion kilometers away. With such vast spaces between stars, the chance of two colliding head-on is extraordinarily small. Instead, gravity will take the lead in this cosmic dance, pulling and stretching both galaxies into sweeping arcs. Long tidal tails will unfurl, curving outward like delicate ribbons of starlight, and from this tremendous merger, a new galaxy will be born. One scientists call Milky Way. Simulations suggest that Milky Way will likely take the form of a giant elliptical galaxy, yet its final shape remains uncertain. Depending on how much gas the Milky Way and Andromeda retain during the encounter, the result might instead be a grand lenticular system, or even a super spiral. Earlier studies from 2012 proposed that the collision was all but inevitable, as Andromeda seemed to have almost no sideways motion relative to its approach. But more recent research from 2025, drawing on precise measurements from the Gaia and Hubble observatories, has softened that certainty. When the gravitational influence of other dwarf galaxies in the local group is taken into account, the likelihood of a collision within the next 10 billion years is closer to 50%. Both the Milky Way and Andromeda cradle a supermassive black hole at their centers. Sagittarius, a star, our own galactic anchor, carries a mass about 4 million times that of the Sun. Andromeda's central black hole is far more massive, estimated between 100 and 200 million solar masses. When the two galaxies begin their slow, inevitable dance, these colossal objects will also drift toward each other, nearing the center of the newly formed galaxy. This long process, unfolding over millions of years, is guided by what astronomers call kinetic friction. As the black holes move, their orbital energy is transferred to surrounding stars, flinging those stars outward while the black holes gradually sink toward the core. Once they come within a light-year of each other, they will begin releasing extraordinarily powerful gravitational waves, ripples in space-time that drain away their remaining orbital energy until they finally merge. The gas drawn into this merging black hole could blaze into brilliance, becoming a quasar or an active galactic nucleus. Such an event may unleash energy equivalent to 100 million supernovae, a final resounding crescendo in the symphony of two galaxies becoming one. In this vast cosmic performance, the fate of our own solar system is a small yet deeply poignant movement. Nature did not design Earth to endure long enough to witness this grand merger. By the time the galaxies approach one another, about 4.5 billion years from now, Earth's surface will likely have grown too hot for liquid water to survive, bringing an end to all terrestrial life. The reason lies close to home: the sun's increasing brightness. In roughly 0.5 to 1.5 billion years, the sun may shine 35 to 40% brighter than today. Such a rise in heat could trigger an unstoppable greenhouse effect. Long before the birth of a new galaxy, our blue world may have transformed into a scorched, barren desert, its once vibrant life merely a memory. Yet even after life has faded, the Earth and the Sun will continue their silent voyage within the evolving galaxy. Simulations suggest two principal possibilities. First, there is a 50% chance that the solar system will be pushed outward to a calmer region, 3 times farther from the galactic center than we are now, leaving us to drift quietly in the serene outskirts of the new Milky Way. Second, there is a 12% chance that the solar system will be cast entirely out of the galaxy. It would become a solitary traveler, moving through the deep silence of intergalactic space, an eternal wanderer. Despite the drama of such a fate, the ejection itself would cause no harm to the planets. The sun would continue to hold its family in orbit, and the planets would circle as faithfully as ever, carrying with them the echoes of a vanished home. A less fortunate possibility has also been imagined. The sun may drift closer to the heart of the newly formed galaxy, into the region where the two supermassive black holes have just become one. There, the sun could be drawn toward this immense gravitational well before being cast outward again. In a far more unsettling scenario, part of the sun itself could be torn apart by the black hole's gravity and pulled into its depths. The Milky Way does not face the distant future alone. It belongs to the local group, a family of more than 50 galaxies. Though separated by immense distances, they are bound to one another by gravity, moving slowly together in a long, patient dance. Over the next 150 billion years, these remaining galaxies will gradually fall into the Milky Way, completing the evolution of our local cosmic landscape. In the end, what we now call the local group will likely become a single, vast, elliptical galaxy, an island of stars floating in an ever-expanding sea of space. And although the Milky Way still carries the material needed to create new stars, the pace has slowed. Its most vibrant era of star formation is far behind us. Tonight we live in a gentler age. The Milky Way, settled into the quiet glow of middle life, continues to form stars with a steady, measured calm. Night travelers, perhaps only a few of you remain awake now, listening to the vast and patient song of the Milky Way. You know that this great galaxy has been singing for more than 13 billion years and will continue long after we are gone. You also know that we, as humans, cannot survive long enough to witness the birth of its next chapter, with melodies even more wondrous than the ones we hear today. Our time is brief beside the great span of the universe, but this is neither a sadness nor a tragedy. As we listen to the music of stars, of planets, of drifting cosmic dust, we remember that the Milky Way has endured a long and tireless journey of creation, transformation, and preparation for an unknowable future. Its quiet harmonies lift us gently into the boundless dark, clear our thoughts, ease the weight of our earthly lives, and guide us toward a place where reason and imagination meet. The Milky Way's melody does not frighten. Instead, it whispers, softly, steadily, without end, leading humanity toward new horizons of knowledge, of wonder, and of peace. Our solar system, with the sun at its center and 8 planets, along with countless smaller bodies, circling quietly around it, is no more than a single grain of sand within a far greater structure known as the Milky Way. This immense home of ours is a barred spiral galaxy, the sun's place. The sun does not reside in the brilliant heart of the Milky Way. Instead, it drifts along one of the outer spiral arms, the Orion's Cygnus arm, sometimes called the local spur. We are situated roughly 24,000 to 28,000 light-years from the galactic center. Even traveling at the speed of light, about 300,000 kilometers per second, it would still take nearly 25,000 years to reach that distant core. From our vantage point on Earth, the Milky Way appears as a vast, slender band of light with a gentle swelling at its center. This flattened form is the result of the galaxy's slow, majestic rotation. The Sun, carrying the entire solar system with it, follows a nearly circular path around the galactic center at a speed of about 220 kilometers per second. One full journey takes roughly 220 to 250 million years. Astronomers call this span a galactic year, and since the Sun was born, it has completed only about 20 such orbits, a reminder of how young we truly are in cosmic time. The Milky Way's barred spiral structure means that a long, luminous bar stretches outward from its core, with graceful spiral arms unfolding into the galactic disk. These arms are not merely decorative, they are regions of ongoing creation, glowing more brightly than their surroundings because they are filled with young, hot, massive stars. Although we live within the galactic disk, Earth's own orbital plane, the ecliptic, is tilted by about 60 degrees relative to the Milky Way's plane, giving us a slightly skewed perspective on our galactic home. At present, our solar system is passing through a tenuous region of space known as the local interstellar cloud. This cloud lies inside a much larger cavity called the local bubble, an hourglass-shaped void filled with extremely hot plasma, likely carved out by ancient supernova explosions. The birth of the solar system, the formation of our solar system, about 4.6 billion years ago, was not a single quiet moment, but the outcome of a turbulent and dramatic process unfolding within the Milky Way. The supernova's touch. The Sun is believed to have formed from the collapse of a small fragment within a giant molecular cloud. This cloud consisted mostly of hydrogen and helium, about 98% of its mass, with the remaining fraction made up of heavier elements forged in earlier generations of stars and scattered into space when those stars died. Inside some of the oldest meteorites, scientists have found traces of short-lived isotopes such as iron-60. Their presence suggests that one or more supernovae exploded nearby around the time the Sun was forming. The shock waves from such an explosion may have compressed parts of the cloud, triggering the collapse that gave birth to our star. The solar system likely formed not in isolation, but within a young star cluster containing perhaps 1,000 to 10,000 stars. The most massive among them lived fast and died young, burning out and exploding within only a few tens of millions of years. The lone wanderers. Over time, the solar system drifted away from its birth cluster and continued its long orbit around the galactic center. In those early ages, close encounters with passing stars were far more common than they are today. Such encounters may have disturbed the distant icy bodies of the solar system, explaining the unusual elongated orbits of objects like Sedna. Some comets and smaller bodies may have been pulled away entirely, cast into interstellar space. Others may have been captured, silent exchanges between passing stars, trading fragments of their distant pasts. Icy dust and ancient echoes. Scattered throughout the Milky Way are stars of astonishing age. Astronomers have identified a group known as SASS, Small Accreted Stellar System, stars within the galactic halo, the vast spherical cloud of stars surrounding the disk. These stars formed 12 to 13 billion years ago, when the first galaxies were just beginning to take shape. What makes these stars remarkable is their extreme lack of heavy elements. Their chemical simplicity suggests that they originated in small dwarf galaxies, later drawn in and absorbed by the Milky Way. Their retrograde motion, traveling opposite to the general rotation of the galactic disk, betrays their foreign origin. The presence of these ancient, chemically distinct stars in the halo tells a quiet but profound story. The Milky Way grew by consuming smaller galaxies, and in doing so, it gathered the raw materials that would one day become stars, planets, and eventually, us. We have gathered and carefully woven together knowledge from many sources, tracing the long and often violent history of our galaxy. As the solar system drifts through the Milky Way, it is not left unprotected. Around it exists a vast invisible cocoon, a magnetic bubble created by the sun itself, shielding us from the cold and hostile interstellar environment. The sun constantly releases a stream of charged particles, known as the solar wind. This ceaseless outflow inflates an enormous bubble that surrounds the entire solar system, called the solar magnetosphere, or heliosphere. This bubble serves as a powerful radiation shield, deflecting a large portion of ionizing cosmic radiation that would otherwise sweep through our planetary neighborhood. Its shape and size are not fixed. Continuously pressurized by the solar wind, the heliosphere is compressed on the side facing the sun's motion through the galaxy and drawn out into a long tail, the heliotail, behind it. Recent studies even suggest its shape may resemble a gently deflated croissant rather than a perfect sphere. At its outer edge lies the heliopause, the boundary where the outward pressure of the solar wind is finally balanced by the inward pressure of interstellar matter. This distant frontier lies roughly 120 astronomical units from the Sun. Both Voyager 1 and Voyager 2, launched by NASA, have crossed this boundary. Their journeys carried them through the termination shock, where the solar wind slows from supersonic to subsonic speeds, then through the turbulent heliosheath, and finally into true interstellar space. Beyond the heliopause, the probes recorded a dramatic transformation. Plasma density increased by nearly 40 times, and galactic cosmic radiation surged. It was a clear reminder that our protective bubble, though vast, is not absolute. Indeed, evidence suggests that about 3 million years ago, the heliosphere temporarily shrank, allowing interstellar matter to reach Earth directly. A quiet but profound encounter between our planet and the wider galaxy. The solar system does not travel alone. It moves within a galaxy whose spiral arms continually reshape our surroundings, not only through gravity, but also through the unseen influence of dark matter. The Milky Way's spiral arms are not rigid structures. They are density waves, regions where matter becomes more concentrated as stars and gas orbit the galactic center. If stars alone defined the arms, they would have long since wound themselves tightly together. Instead, stars and gas drift in and out of these dense regions. When gas enters a density wave, it is compressed, triggering the birth of young, bright, massive stars that briefly illuminate the arms. Our sun resides not within a major arm, but in a quieter interarm region, an armlet or spur, situated between the Sagittarius and Perseus arms. The graceful motion of the Milky Way is governed not only by what we can see, stars, gas, and dust, but also by an unseen presence, dark matter. Astronomers infer its existence through the galactic rotation curve. Stars far from the galactic center move just as fast as those closer in, defying expectations. This steady speed implies an unseen mass distributed throughout the galaxy's halo, an invisible gravitational backbone holding everything together. Near our own position in the galactic disk, the local density of dark matter is estimated at approximately 0.43 plus or minus 0.02 giga-electron volts per cubic centimeter. At the galaxy's heart lies another mystery, an unexplained excess of gamma rays, known as the galactic center excess. Two main explanations remain under consideration. One points to a dense population of rapidly spinning pulsars. The other suggests dark matter particles colliding and annihilating one another. Early studies favored pulsars, but later analyses revealed gaps and uncertainties, reopening the dark matter possibility. Should dark matter prove to be the source, it would mark the first evidence that it interacts with visible matter through forces beyond gravity alone. Though the solar system has remained remarkably stable for billions of years, it is not immune to change. Gravitational interactions continue to shape its future, which will ultimately be determined by the life cycle of the Sun and by vast galactic events yet to come. On very long timescales, even the orderly orbits of the planets reveal a subtle chaos, a reminder that nothing in the universe, no matter how familiar, is ever truly still. And so, as we sit quietly here, listening to the low hum of the cosmos, the solar system continues its journey, protected, influenced, and forever shaped by the larger galaxy that carries it along. Millions, and even billions of years pass. Over such immense stretches of time, order slowly gives way to chaos, most clearly revealed through gradual but profound changes in the shapes of planetary orbits. Among all the planets, Mercury is the most fragile. Over the next 5 billion years, its orbital eccentricity may increase significantly, with a small but real chance, about 2%, of instability. In such a future, Mercury could spiral into the Sun, collide with Venus or even Earth, or be cast entirely out of the solar system. Though rare, stellar flybys remain a quiet danger. Roughly once every 100,000 years, a star may pass within about 0.8 light-years, nearly 50,000 astronomical units, of the Sun. Such encounters can disturb the distant Oort cloud, sending comets and asteroids inward, increasing the likelihood of impacts on the inner planets. Far ahead in time, the solar system faces an inevitable possibility, an encounter with its nearest large neighbor, the Andromeda Galaxy. Andromeda is approaching the Milky Way at roughly 120 kilometers per second. Earlier models predicted a collision in about 4 billion years. Yet despite the dramatic name, this would not be a catastrophic crash. The distances between stars are so vast that the chance of a direct stellar collision, including one involving the Sun, is essentially zero. This event would not destroy our planetary home. Still, subtle consequences may follow. Radiation levels could increase near active regions of the newly formed galaxy. Gravitational disturbances from passing stars might again stir comets and asteroids from the outer reaches of the solar system. More recent studies, using refined data from the Hubble and Gaia observatories, suggest uncertainty remains. The probability of a direct merger within the next 10 billion years may be closer to 50%. In many simulations, the two galaxies merely pass one another at a distance of several 100,000 light-years. Whether galaxies collide or drift apart, the ultimate fate of the solar system lies with the Sun. In roughly 1 billion years, the Sun's brightness, slowly increasing by about 1% every 100 million years, will overheat Earth. Carbon dioxide levels will fall too low for photosynthesis, bringing most life to an end long before the Sun expands. Around 5 billion years from now, the Sun will exhaust its hydrogen fuel and swell into a red giant. It will lose nearly 30% of its mass and expand to more than 250 times its current size. Mercury and Venus will almost certainly be consumed. Earth's fate remains uncertain. Its orbit may expand outward, but tidal forces and the Sun's bloated atmosphere could still draw it in. Eventually, the Sun will shed its outer layers, forming a glowing planetary nebula. What remains will be a dense white dwarf, roughly the size of Earth. Over unimaginable spans of time, it will cool further, fading into a silent, theoretical black dwarf. Long after the Sun's death, the remnants of the solar system will continue to drift through the galaxy. Yet even then, time has the final word. Gravitational encounters with passing stars will slowly unravel the remaining planetary orbits. Calculations suggest that after roughly 1 quadrillion years, these interactions will completely separate the planets from their dead star. At that moment, the solar system, at least in any meaningful sense, will no longer exist. And so, our journey through the grand dance of the solar system and the Milky Way comes to its quiet close. From a violent birth sparked by ancient supernovae, through the protection of a magnetic bubble, to the slow fading of the Sun across billions of years, this story reminds us that we are inseparable from the vast universe that surrounds us. Now, let us drift gently into sleep, carrying thoughts of giant stars, cold clouds of dust, and the distant fate of the worlds that circle them. Everything in the universe has its rhythm. Relax. Let the tension slip from your face, your shoulders, your feet. Allow your thoughts to grow lighter, like a single grain of dust drifting freely through weightless space. Listen closely to the quiet whispers of the galaxy's vastness and complexity, and let this slow, ancient story of creation carry you gently towards sleep. Tonight, we will think about dust, not as something ordinary or unclean, but as something sacred. Dust is the precious remnant of dead stars and the quiet beginning of all life. Let us turn the clock back to a time nearly 4.6 billion years ago, when our solar system did not yet exist. There was no sun, no planets, only a vast, cold expanse of space known as a giant molecular cloud. This immense cloud stretched across tens of light years, like a frozen snowfield under an eternal night sky. Known as the pre-solar nebula, it was composed mostly of hydrogen and helium, about 98% of its mass, mixed with a faint but vital trace of cosmic dust. Dust in space is nothing like the dust in our homes. These are microscopic grains of solid matter, rich in heavier elements, what astronomers call metals, forged in earlier generations of stars and scattered when those stars reached the end of their lives. Though this dust made up only about 2% of the nebula, it would become the most important ingredient of all, the foundation of rocky planets, including Earth. This enormous cloud did not collapse by chance. Within the oldest meteorites ever discovered, scientists have found traces of short-lived radioactive isotopes, such as iron-60. Their presence is a clear signature of nearby supernova explosions, stars that lived fast, died young, and ended in violence. The shock waves from one or more of these explosions swept through the cloud like a decisive breath of fate, compressing the gas and dust. Balance was lost, gravity took hold, and collapse began. As the cloud contracted, a simple but unyielding law of nature, conservation of angular momentum, caused it to spin faster and faster. The collapsing material flattened into a vast protoplanetary disk, nearly 200 astronomical units wide. At its center, most of the matter gathered into a glowing newborn protostar, the young sun. Within the disk, gas and dust moved in slow, graceful spirals. Over millions of years, tiny grains collided, clung together, and grew. Gravity patiently stitched them into larger bodies called planetesimals, the quiet ancestors of planets. This process, known as accretion, is slow and deliberate. Dust becomes pebbles. Pebbles become rocks. Rocks become worlds. It is construction on a cosmic scale, guided by time rather than haste. As in any fire-lit room, temperature matters. The farther one moves from the young sun, the colder the disk becomes. This gradual change created a boundary with profound consequences, the frost line. Close to the sun, temperatures were too high for water, methane, or ammonia to freeze. Only materials with high melting points, rock and metal, could survive as solids. These materials were scarce, forming less than 1% of the nebula's mass. As a result, the planets that formed here remained small and dense: Mercury, Venus, Earth, and Mars. Farther out, beyond roughly 5 astronomical units, temperatures dropped enough for ice to form. Water, methane, ammonia, and carbon dioxide froze into solid grains. Ice was abundant, allowing planetary cores to grow rapidly. Once these cores became massive enough, they drew in vast envelopes of hydrogen and helium, becoming the giant planets: Jupiter, Saturn, Uranus, and Neptune. Every object in the solar system, whether dust grain or giant planet, was shaped by gravity and temperature. The sun's heat and solar wind stripped volatile materials from the inner planets, leaving them dry and compact. Earth, dense and resilient, became the heaviest of the rocky worlds. These chemical differences remain the greatest legacy of the protosolar nebula. When the Sun finally settled into its long, stable life as a main sequence star, its radiation and solar wind swept away the remaining gas and dust. The era of planet formation ended, but countless fragments remained behind. Even now, the solar system is not empty. It is filled with a thin veil of interplanetary dust, created by crumbling comets and colliding asteroids. On the darkest nights, far from city lights, this dust reveals itself as the zodiacal light, a faint triangular glow rising gently from the horizon. Some of this dust may come from asteroids. Other studies suggest that even Mars has contributed material to this drifting cloud. Between Mars and Jupiter lies the asteroid belt, a broad ring of debris stretching from 2.3 to 3.3 astronomical units from the Sun. This is not a crowded minefield, as fiction often suggests, but a vast and sparsely populated region. All the asteroids combined weigh less than 5% of the Moon. This belt is the remnant of a planet that never was, its growth disrupted by Jupiter's immense gravity. Ceres, the largest object in the belt, stands apart. Discovered in 1801, it is massive enough to be round, earning its place as a dwarf planet. Its surface is rich in carbon, ice, and hydrated minerals. Beneath that surface, Ceres may hide a layer of salty water or muddy brine. Images from NASA's Dawn spacecraft revealed bright, reflective patches, likely salt deposits left behind as ancient water slowly evaporated. Vesta, the second largest body in the belt, tells a different story. It is not merely a pile of rock, but a differentiated world, with a core, mantle, and crust. Once, it was hot enough inside to melt and separate into layers, much like the terrestrial planets. From drifting dust to fractured worlds, these remnants are the surviving witnesses of a turbulent beginning. Each grain, each stone, carries within it the memory of the solar system's earliest moments, a time of chaos, creation, and quiet perseverance. The Milky Way, our vast and familiar home, is a barred spiral galaxy. Its very existence stands as a quiet yet powerful testament to how dust and gas can be shaped, organized, and sustained on a scale far beyond human imagination. Our Sun does not reside in the dazzling heart of the Milky Way. Instead, it drifts in a calmer neighborhood, along one of the outer spiral arms known as the Orion Cygnus Arm. From here, we are approximately 24 to 28,000 light-years away from the galactic center, where a supermassive black hole lies hidden in darkness. Even if one could travel at the speed of light, the journey inward would still take around 25,000 years. The spiral arms of the Milky Way are not rigid structures or permanent collections of stars. Rather, they are regions where matter becomes more densely packed, what astronomers call density waves. One might imagine them as slow, gravitational ripples moving through the galactic disk. Stars, gas, and dust do not remain fixed within these arms. They drift in and out of these denser regions as they orbit the galactic center. When clouds of gas enter a density wave, they are gently but firmly compressed. This compression ignites the birth of young, massive, and brilliant stars, briefly lighting the darkness. What is truly remarkable is how dust and gas arrange themselves within these spiral arms, forming a layered structure, orderly, precise, almost architectural. Each spiral arm is divided into parallel lanes, with different materials occupying distinct regions. Along the inner edge of an arm, closest to the galactic center, gas first encounters compression. Here, dust is heated, glowing faintly as a signature of the shock it has endured. This hot dust consistently lies closer to the center than the cold molecular gas. The middle of the arm contains cold carbon monoxide gas and active star-forming regions, where stellar nurseries quietly operate. Farther outward, the arm fades into a population of older stars. This repeating pattern, hot dust at the inner edge, cold gas at the center, and aging stars beyond, is not coincidence. It is the first clear and sufficient evidence supporting the galactic density wave theory. The spiral arms are not random decorations, but the result of a carefully choreographed dance between gravity and matter. The solar system itself is more than a family of planets circling a star. It exists within a protective enclosure, gently inflated by the sun. The sun continuously releases a stream of charged particles, plasma, known as the solar wind. This outflow creates a vast invisible shell around the solar system, the solar magnetosphere, or heliosphere. This magnetic bubble shields the planets from a significant portion of the galaxy's ionizing cosmic radiation. Form. Its shape is complex and ever-changing, sometimes likened to a comet, and more recently to a softly deflated croissant drifting through space. Boundary. The outer edge of this bubble, where the outward pressure of the solar wind meets the inward pressure of interstellar space, is known as the heliopause. The heliosphere is not stationary. It moves through a region of space called the local interstellar cloud, itself embedded within a larger cavity known as the local bubble. This local bubble is filled with hot plasma and is believed to be the aftermath of several relatively recent supernova explosions. Evidence suggests that around 3 million years ago, the heliosphere temporarily shrank, allowing interstellar material to reach Earth directly, an event that may have left subtle marks on our planet's climate. The Milky Way's complexity extends far beyond what we can see. Beneath the stars lies dark matter, silent, unseen, yet essential. Dark matter forms the galaxy's invisible gravitational framework, determining how fast stars orbit, especially at the outer edges where visible matter alone cannot explain their steady speeds. Near our location, its density is estimated at approximately 0.43 giga-electron volts per cubic centimeter. At the galactic center, an enigmatic excess of gamma rays, the galactic center excess, has been detected. One possible explanation is that dark matter particles are colliding with one another. If confirmed, this would mark the first evidence that dark matter interacts with the visible universe through forces beyond gravity alone. Though the Milky Way unfolds on a grand scale, transformation also occurs deep within individual worlds. Far beneath the clouds of Uranus and Neptune, extraordinary processes may be unfolding. Under immense pressure and extreme temperatures, methane molecules are thought to break apart. The liberated carbon atoms are compressed into microscopic diamonds, which may fall slowly through the planet's interior like silent, glittering rain. And so, from the vast spiral arms of the galaxy to diamond rain hidden inside distant planets, the universe continues its quiet work, layered, patient, and profoundly ordered, while we listen in the stillness of the night. Diamond rain drifts downward, falling gently yet relentlessly toward the deep heart of the planet. This remarkable phenomenon, often called diamond rain, is believed not to be unique. Similar processes may also occur within the immense interiors of Jupiter and Saturn, hidden far beneath their turbulent clouds. Even the most magnificent structures in the solar system are not eternal. Saturn's rings, as luminous and delicate as they appear, are composed primarily of countless particles of water ice, and they too are slowly fading. Under the influence of Saturn's gravity and magnetic field, these icy particles are gradually drawn inward, falling onto the planet in a process known as ring rain. Careful observations suggest that within a few 100 million years, a brief moment on a cosmic clock, Saturn's iconic rings may vanish entirely. Across the solar system, dust leaves its quiet fingerprints on entire worlds. Mars owes its familiar red hue to fine grains of iron oxide, rust blanketing its surface. Over billions of years, iron-rich material reacted with the planet's thin atmosphere, slowly painting the planet in shades of red. Venus, by contrast, is a world of extreme heat, where surface temperatures reach around 464 degrees Celsius. This inferno is the result of a runaway greenhouse effect, caused by its dense carbon dioxide atmosphere. Yet beneath this harsh exterior lie intriguing hints of a gentler past. Scientists are closely examining Venus's tessera terrains, complex, elevated regions whose mineral composition suggests the presence of plate tectonics and, long ago, oceans of liquid water. The iron oxide dust of Mars and the felsic crust of Venus are more than surface features. They are enduring records of complex chemical and geological processes, silent witnesses to the long transformation of cosmic dust. Together, they form the next chapter in the story of how simple stardust evolves into worlds, each shaped by time, chemistry, and the quiet persistence of change. Far beyond Neptune's distant path lie silent, frozen realms, icy kingdoms that preserve the most primitive material of the early nebula, locked away as ancient dust and ice. The Kuiper Belt is a vast ring of icy bodies stretching from roughly 30 to 50 astronomical units from the Sun. It resembles the asteroid belt in structure, yet it is composed primarily of frozen dust and volatile ices. Within this distant region dwell countless small worlds, including the dwarf planets Pluto, Eris, Haumea, and Makemake. Ancient remnants. These objects are time capsules, survivors from the very dawn of the solar system, largely unchanged for billions of years. Mirror surfaces. Some Kuiper Belt objects possess astonishingly bright surfaces. Haumea, for instance, a rapidly spinning, elongated world, is coated in crystalline water ice that reflects sunlight like polished glass. Farther still, beyond even the Kuiper Belt, lies the Oort cloud, a vast theoretical sphere composed of perhaps 1 trillion icy bodies surrounding the solar system like a distant halo. This remote cloud is believed to be the birthplace of long-period comets, objects cast outward by the gravitational influence of the giant planets. The Oort cloud may extend nearly a full light year from the Sun, marking the true outer boundary of the Sun's gravitational reach. When a comet, an icy traveler from the Kuiper Belt or the Oort cloud, ventures into the inner solar system, the warmth of the Sun awakens it. Ice turns directly into gas, releasing dust that has been frozen since the beginning of time. This escaping material forms a luminous tail of gas and dust, stretching across the sky. Curiously, the tail always points away from the Sun, regardless of the comet's direction of motion, a gentle reminder of the constant pressure exerted by solar wind and sunlight. In the fullness of time, even the finest grains of matter will disperse. Thus concludes the great cycle of creation that began within the primordial nebula. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. It will swell into a red giant, expanding outward to engulf Mercury, Venus, and perhaps even Earth. Planetary nebula. As the Sun reaches the end of this phase, it will shed its outer layers. Enriched with elements such as carbon, this glowing shell of gas and dust will form a planetary nebula. This material will return to the interstellar medium, recycled and prepared to give rise to future stars and planets. What remains at the center will contract into a white dwarf, a dense, Earth-sized ember of stellar matter. Even after the Sun's death, the remnants of the solar system will persist for an almost unimaginable span of time. Chaotic gravitational encounters. Over eons, the subtle gravitational influence of passing stars within the Milky Way will slowly disturb the orbits of the remaining planets. The final purge. After approximately 1 quadrillion years, these accumulated interactions will strip the last planets away, sending them adrift into interstellar space. At last, the solar system will fade entirely from existence. The final white dwarfs will cool into hypothetical black dwarfs, cold, dark remnants, silent witnesses to a universe that has moved on. And so, the dust returns to sleep, waiting, patiently, for the next beginning. Good night, night travelers. May the universe's stories ease your mind, and may its quiet light guide you into restful sleep. Goodbye.